I'd like to thank the organizers for inviting me to speak and also inviting me to this workshop. I've been learning a lot so far. So the goal of this talk is really to ask a specific question. And so there's many questions in life, and so the content of this talk is going to try to formulate this question and explain why it's interesting. So the question lives in the world of classical automorphic forms. So over a number field, I will write larger. Okay. So automorphic forms, I mean functions on the automorphic space, which I was to be denoting by bracket G of G of A mod G of F. But so the motivation is going to be coming from this more evolved geometric theory of automorphic forms, which Tony kind of mentioned in a previous talk, but I'll review it again here. So firstly, you have an analogy between number fields and function fields. So here you have so a function field means the field of rational functions on some smooth projective curve over a finite field. And now if you restrict to only the unramified functions, so that means you look at this bracket G, but now you consider the orbits over this maximal compact. So here, all the V is going over all of the closed points of your curve, and O sub V means the completed local ring at that place. So they observed that this is the same as the rational points on this moduli stack Bun-G. So Bun-G denotes the moduli stack of G bundles. On this particular curve X. So this is some geometric object, and kind of for the purpose of this talk, basically, we can think about Bun-G really just as this automorphic space. But so now that we have this geometric object, so over a finite field, we can use the function Sheaves dictionary. So this is Grothendieck's function Sheaves dictionary. So from a sheaf, you can look at trace of Frobenius, and you can get a function. So the dictionary now lets us go from functions to L-adic sheaves. And so here, our curve is still over a finite field. And now, so one last step in this process is that from L-adic sheaves, you have, so tilde will mean analogy. So you have an analogy between L-adic sheaves and D modules. So if you stuck with finite field, then if you restrict it to perverse sheaves, then the analogy kind of is an actual equivalence by Riemann-Hilbert. But so for certain reasons, you may want to consider kind of not just perverse sheaves or like some larger category. But also, so in the setting of D modules, we really want to be working with kind of curves over the complex numbers. And so now this kind of tilde becomes an actual analogy. And so we went from automorphic forms on a number field to D modules just because here, this is where kind of the geometric Langlands program lies. And so this was originally championed by Drinfeld and Lemon, and now is worked on by many other people. So we won't really need to talk about the specifics of this, but the idea is that kind of in the geometric Langlands, because you have sheaves and all these geometric objects, you should be able to see more than at the level of functions. And so the overview of kind of where this question I want to describe comes from is that, so in the setting of geometric Langlands, so Drinfeld and Gaitsgory defined and, well, first they defined a particular functor, which can be thought of as a renormalized Verdier duality. So REN stands for renormalized. So they showed it D here means the category of D modules, but we can just think about it also as some derived category of L-adic sheaves. So the check means some kind of dual category, but so it just means it's slightly different. It's between a category and its dual, but just really the idea is that somehow on a sheaves you have Verdier duality, but this is not exactly Verdier duality, but something close. So first, they showed that you can define this thing, but more importantly, it's an equivalence of categories. And so they also show that from the perspective of geometric Langlands, this is kind of a really fundamental equivalence to consider. And so basically, somehow, like, it's unavoidable to consider this equivalence, even though, like, the definition is maybe a little surprising. So now, if we kind of work in this box of L-adic sheaves, so now if you use functions sheaves dictionary, this means that, so I said, kind of Bungie, you really just think about as the automorphic space. Then just using the dictionary, we're going to get like an actual operator that goes from unramified compactly supported functions on bracket G to just all smooth functions. And so for the slightly surprising thing that I'm going to be talking about in this talk is that, so right now this is over a function field, but it turns out that like you can generalize this definition in a way so that it makes sense to define as an operator that goes from the short space of automorphic functions over any global field to the space of automorphic forms. Yeah. So kind of this is over any global F. So the choice of the letter L is totally arbitrary. Just at some point, I ran out of letters, and you look around, and that was the only one left. So kind of this side. So kind of this would be, you can think of it as some kind of completion of this. Yeah, so there's some kind of, this is like a smaller subset of the big guy, but the check kind of changes support conditions. So yeah. The right should be the analog of automorphic forms. Well, it's not smaller, but kind of you can always like define it on a smaller category. It's just that like these two things are generated by have different generators. Right, but I was like, if you define an operator on something smaller, you can kind of complete it to some larger space. That's kind of the idea here, is that to get the equivalence, you complete it so that both sides. But somehow in this world, it's hard to, like, you can't really describe the completed guys classically. But just, we'll see later, like, so later we'll see that this is kind of an injection, and then you can explicitly describe what the image is, which is smaller than the entire space. So you can think of this as, this line is really saying you're going from some kind of smaller generating subspace of the left to a smaller generating subspace of the right, but these are not the same. And the check is kind of specifying that these two things aren't generated by the same functions. Okay. So the question really is, what role does this operator L play in the classical theory? So I still don't know the answer to this question. So it's an actual question. But so, before I even define it, let me just note that if you restrict to just the cusp forms, then this operator is just identity. So it's not so, like, you're not going to get anything interesting on cusp forms, so really this is just something dealing with Eisenstein series in a particular way. Okay, so even though kind of the origins are from this geometric Langlands picture, so in geometric Langlands there's like lots of categories and technical complications. So instead I'm going to start by just defining this operator L from the classical side. And kind of the point is that a lot of these things, like, we can see it just in the classical picture anyways. So like I'm starting by defining this operator L, and it's just, it'll maybe seem a little like I'm like arbitrarily pulling out this definition out of nowhere, but just remember that kind of it did come from some geometric idea that I will explain afterwards. So F will be a global field, and A denotes the dels. And so for the purposes of this talk, G is just going to be SL2. And so in general, so G is split connected reductive. But But so there is the caveat that, so there is some analytic result for the general G that I haven't checked in the number field case. So like for function fields, there is no analysis going on, and everything is kind of combinatorics and kind of questions about different cones and lattices. So basically, everything has been checked for function fields, which means that all of the combinatorial issues have been settled. But I'll point out there's some like analysis that needs to be done in the number field case. So I'll use curly A to denote the space, or for me, a particular space of automorphic forms, but I'll mean smooth K finite. K is the standard maximal compact. So for SL2 and the rationals, it's SO2 times SLO for all the places. So smooth K finite functions with uniform moderate growth. On bracket G. So uniform moderate growth means that all of the derivatives are bounded by kind of the same polynomial. And so inside here, we have the Schwartz space. So this will be smooth K finite functions and now with all derivatives rapidly decreasing. Well, so at the cusp. So kind of in the usual picture, there's kind of only one direction, and you want your function so that, well, when you take all derivatives, it's rapidly decreasing as you're going in this y goes to infinity direction. So now this operator L is going to be taking Schwartz functions to the space of automorphic forms. And so there is already a candidate for such an operator, and that candidate is just the identity. So L is not the identity. Well, so by identity, I mean this like natural inclusion of Schwartz functions into all automorphic functions. But it's also not so far from the identity, meaning that this operator, kind of you modify the identity by boundary contributions. And so boundary terms here means you take the constant term of some function, and well, then you use kind of pseudo-Eisenstein series to get back to automorphic forms. So to define these boundary contributions, let me briefly review constant terms and pseudo-Eisenstein series. So probably everyone knows the definitions, but since I'm working in this slightly different setting where I'm not fixing, or I'm not working with eigenforms, and also there's, like, the important thing is there will be some kind of strange support conditions. So like the review will be more to highlight those aspects. And so I'm just going to do it for SL2. But again, like relevant combinatorics like can be worked out or have been worked out for general G. So constant term operator takes some automorphic function and sends it to what I'll be denoting C sub B, which is smooth k-finite functions on G of A mod T of F U of A. So the definition is that you're just integrating over U of A, U of F. But I find it helpful to think about it as in this more geometric way where, so you start with some function on kind of the automorphic space. So this is like G of A mod G of F. And then you pull it back to a function considered as just G of A mod N of F. So only modding the translations, horizontal translations. And then you push forward, or in other words, integrate along the horocycles. So now you just get just the vertical line. Oh, well, so this picture is just for F equals rational numbers. But so the idea is that constant term is really some kind of pull-push of functions. And so from this picture, what you want to note is that if you started with some function that's kind of compactly supported, so then that means that like the support is going to be below some x-axis. So then when you do this pull-push, the resulting function, the constant term, is going to only be supported in kind of the downward direction, so near 0, and it's not supported near infinity. So and so an analogous statement holds if you replace compactly supported by short functions. So the fact is that if you restrict the constant term to the short space, then it'll land inside like this subspace I'll call C minus. So this means functions in C that are rapidly decreasing, well, all derivatives rapidly decreasing in the y goes to infinity direction. So kind of C, functions in C have two directions, y goes to infinity and y goes to 0. And if you consider Schwartz functions inside here, you would want rapidly decreasing in both directions, but I'm going to separate those two conditions into two subspaces. And so on the other hand, so this is the constant term, which kind of is thought of as some kind of boundary contribution for your function. And then we have the adjoint operator, which goes from, I'll call it just compactly supported functions or Schwartz functions inside C sub B to the entire space of automorphic functions. So this Moglen-Walls-Perget, call this pseudo-Eisenstein series. So kind of the definition you can think of as just, now we're starting from here, and you do like a pull-push in the opposite direction to get something back on the automorphic space. But this is equivalent to the usual definition where you just sum over lattices. So similarly to how a constant term really lands in this C minus guy, you can check that like Eisenstein's, this pseudo-Eisenstein series, it'll converge not only for these compactly supported guys, but as long as you start with something in C plus. So this means the rapidly decreasing as y goes to 0 direction. Sorry, I think well, I think, did I not say? So I guess C should always be moderate growth everywhere. I don't think I wrote that. But other than that, I don't think you need any other condition. Mainly because so kind of these two are adjoint operators, so kind of you can, whenever you can, as long as you can integrate this guy with this C minus, then you're okay. So yeah, Eisenstein series, you can define it on this opposite subspace. So now the picture is that we started with some Schwartz function, and then you can take constant term and it'll land in some kind of C minus. And on the other hand, so let me use the opposite Borel, but that's not so important. If you have C plus, you can take Eisenstein operator and get back to automorphic functions. Yeah. Let me just say. And so we said that L is something that goes from here to here. So really we just want some operator that goes between these minus and plus spaces. And so when you have some kind of, or this space that depends on the Borel and an opposite Borel, like there is this the standard intertwining operator. But so as we'll discuss now, so the standard intertwining operator kind of goes in the opposite direction. Yeah, so this is a minus, meaning this is the opposite Borel. Yeah, so this is to get so intertwining goes from Borel to its opposite, which is why it's needed. So I'll just skip so the fact is that the operator is really defined between these two spaces. So the definition is you have something kind of that was G of A mod U minus of A mod T of F. And so if you want something that's invariant under U of A, you just integrate over the unipotent radical. But so note that unlike the constant term and everything we talked about before, this is just integrating over the Delic points of U, so it's really a product of local integrals. So the quality is in quotes because the local integral is well, it's over G mod U minus of F, so there's no, like the global space had a invariance under T of F. So the spaces are slightly different, but essentially this global intertwining operator is just a product of the local ones. And so this is usually when you see intertwining operator, it's once you fix the character. But here, kind of, I'm considering these slightly different spaces where I'm not fixing the character. And the relation between the two is kind of by Mellin transform. So the R here stands for radon transform. So because in this particular case where G is just SL2, then SL2 mod unipotent radical just identifies with the affine plane with the origin removed. And so now if you look at the local intertwining operator, what it's doing is you're just taking some function on the affine plane, and this operator is really just integrating along hyperplanes. So hyperplanes of an affine plane also identifies as just the affine plane. But so it's slightly non-standard because we don't consider hyperplanes. So in usual radon transform, you consider any hyperplane, but here we don't consider the ones that go through 0. So the point is kind of this, well, this formulation is both non-standard kind of from number theory because we don't fix a character, and it's also slightly non-standard from geometric analysis because we have this, because we're considering G mod U, we have this kind of punctured condition. But so the analytic result is that for G equals SL2, this global operator once you define it between these two particular spaces, is an isomorphism. And also, so because it's SL2, you can give explicit formulas for each of the local. So the way it's proved is you really first prove that all of the local operators are also isomorphisms. And so at each place you can show that give an explicit formula for the inverse. Yeah, so those were because if you take all of these spaces and you tensor them over all the v's, you don't get this guy. So the quotation is in this sense that you can't, I guess, you tensor and then you kind of restrict to this global space. Right, yeah. I guess that's like also something like, I guess part of the, I guess in this case, there's just no convergence issues. And then here, that's kind of part of the information about the local inverses is that when you put them together, there's no convergence issue. Right. No, not, yeah. Yeah, so the quote is really like a quote. Yeah, maybe. I always think about that. I will talk about something else that might be related to this, because there's something local that looks similar, but I hadn't thought about just defining this operator locally. Okay, so let me just give some remarks, not really about, sort of about the proof, but more about kind of the things that this inverse intertwining operator is related to. So firstly, in the Archimedean case, so this, I guess even before that, let me say that here, K finiteness is very important. So both at the non-Archimedean and at the Archimedean places, you really need the K finiteness, otherwise this isomorphism is not true. And so at the Archimedean places, the kind of technique for proof is you basically use Mellin inversion and so there's known formulas for intertwining operator once you do fix the character and for a particular K type. So I think they were known earlier, but so the references are Wallach's article in Corvallis, and also, so in the complex case, there's an article of Duflo. But I think, so both were, it was not the first place it was known, but I just, these were the most available references. But so now, let me say so you can, the statement kind of is general for any parabolic. You just do a parabolic and its opposite, and you say so for any g, this is where, like I haven't checked it in the Archimedean case, but so it's checked if you restrict to unramified functions. Sorry? Arbitrary p. So it's okay on unramified functions. So this is kind of, I don't think it'll be clear from what I've said, but it follows from the Gindikin-Karpelovich formula. And here you can use Harishchandra transform. So the kind of the specialness of unramified is that you have the Harishchandra transform. And like I have an idea, or like a way to generalize the method, because so there are formulas. So for more general, not just unramified functions, there are formulas of Knapp and Zuckerman. So but there's like some analytic, or you need to be careful about like how to state the analytic things. But so now if the field is non-Archimedean, kind of one, like this, everything is proved, but also it's related to some interesting other work. So in this case, let me just say that here, if you consider, if you're looking for like a way to describe the inverse, then the integration kernel of this inverse so this as an object is just a distribution on, so you want to go from G mod U minus to G mod U, so it's just some distribution on the product, but the intertwining operator is kind of twisted equivariant with respect to the levy. So M here denotes the levy of parabolic P. So you're kind of looking for some distribution here. And so the relation is that kind of, so in the group case, Bezirkovnikov and Kazhdan's, and so also in a more general spherical variety case, Saklaridis and Venkatesh. So they study some kind of asymptotics operator that goes from so they studied an operator that just goes from from distributions on G to distributions on this boundary guy. All right, this is F. And so geometrically, you can think of this as this is some kind of boundary degeneration of G, which is, or you can think of G as a symmetric space. And so asymptotics is some kind of nearby cycles type operation. And so the relation between like this intertwining operator and this asymptotics is that if you take the asymptotics as just the delta function at the identity in your group, this is the integration kernel for the inverse. So this kind of inverse radon business is really something about degenerating functions like on a symmetric space. Okay, so now with this result, we can finally come to the definition of L. So it's just defined as, or so this is in the case of SL2. But as I said, you start with identity, but now you modify it by taking a constant term, and then you compose with this inverse intertwining operator, and you send it back to automorphic forms by taking pseudo-Eisenstein series. So this is going from Schwartz functions to automorphic functions. And so in general, this will be an alternating sum over all the standard parabolics. But you can characterize it as follows. So for a cusp form, since the constant term vanishes, it's just identity. And now, so for SL2 besides the cusp, you just look at the image of the pseudo-Eisenstein operator. So L is just going to switch this Eisenstein operator with some kind of opposite Eisenstein operator if phi is, for example, compactly supported. Sorry, there's a minus. And so this Eisenstein and Eisenstein minus with this intertwining guy. So by the usual functional equation for Eisenstein series, it actually tells you that these two operators that I put in brackets have the same, or analytically continue to the same Mellin transform. So they almost look the same, but since this is actually not actually defined on like pure Eisenstein series, like the difference is some kind of shift in contours. Yeah, I keep forgetting to say this. Yeah, so it's compatible with Hecke operators. Yeah, I was just going to, yeah, so that's what I, so this is, somehow only an analogy. And yeah, it would be interesting if like there was a direct relation. Yeah, so and also so you can, this result makes analogy a little more precise. So firstly, as I mentioned earlier, so L is an injection. And so if you let the image, so this is PSC, which stands for pseudo-compactly supported, but this was more notation from function field since nothing is compactly supported over a number field. But so if you let this denote the image, then you can explicitly describe it as the functions in A, where the constant term actually lands in the space C plus. So recall that, recall slash fact is that, well, for SL2, the short space can be described as just the functions in A where the constant term lands inside C minus. So somehow A is this subspace where you actually want the constant terms like to have behavior near the boundary, but you don't want it to have behavior somehow like in the more like normal part. Okay, so this is part of it, but now also, so if you started with some function inside the image, there's actually a very simple formula for the inverse. And so this is like the more direct analog of Aubert involution. So kind of when you look at the inverse, there's actually no intertwining going on because kind of it lands in the part where Eisenstein series does converge. So you just literally take constant term and then apply Eisenstein. But let me, for reasons of time, actually explain where this L guy comes from. So we established so this operator is an equivalence between two kind of different subspaces of automorphic forms. And so it kind of, again, you can ask what the integration kernel for L. So this is just the distribution on two copies of bracket G. But if we restrict to just unramified functions, so then the kernel is a distribution, well, because it's unramified, it will actually identify with a smooth function. So the kernel is just some element which I'll denote little b inside C infinity of G times G. That's K times K invariant. And so now by Wei, like functions on this guy are the same as just functions on two copies of rational points of moduli stack of G bundles. So the result joint with Drinfeld for the SL2 case, and then in a separate paper for general split G, is that this integration kernel really just comes by function sheaves dictionary. So it's the trace of geometric Frobenius of this L-adic complex on two copies of Bun G. So here delta denotes the diagonal map from one copy of Bun G to two copies. And QL bar just means the constant sheaf on one copy of Bun G. But, okay, so this still seems kind of random because you just pick some random sheaf and then took the trace of Frobenius. But one note is that if you considered, so kind of in geometry you see more in that kind of you have more functors. So if you considered like delta lower Schriek, then by Grothendieck-Lefschetz trace formula, so this will also define some kind of integration kernel, and the operator you get is just the identity from the short space so the identity inclusion to automorphic functions. So like somehow this is only slightly different from the identity as we kind of already established at the level of functions. But so why do you want to consider delta lower star? So essentially, what Drinfeld and Gaitsgory do kind of basically in a categorical setting is you just like use delta lower star like really as the integration kernel, but at the level of like derived categories to define this functor, which I denoted by kind of renormalized Verdier duality. And so they show, they show that this is well defined because for delta lower star, you basically show things that amount to convergence issues. But then they show that it's an equivalence. And so the remark is that if you do the same thing with delta lower Schriek, so what you get is just the usual Verdier duality. But so the very surprising thing that kind of amounts to like the automorphic space not being compact is that this Verdier duality is actually not an equivalence. So this was kind of one of the origins of why this operator came up is that, well, you expect Verdier duality kind of to be an equivalence of categories, but also, so this is kind of just the automorphic side. Let me just draw some arrows. But so it's kind of believed, like you have geometrical language which says that the automorphic side is supposed to correspond to some kind of spectral side. So Loxis is like the characteristic zero analog of Galois representations. And then, well, QCO is somehow you arrange them in continuous families. But so the prime means that this is not really the right space, but it's something much nastier. But the content here is just, so on the spectral side, like for any quasi-coherent sheaf, you expect, or there is a Serre duality. And so on this side, you have just Serre duality, and there's no problems, and it does give you an equivalence. And then you'd expect that radiate duality kind of matches by geometric Langlands Serre duality on the automorphic side, but like equivalences should match equivalences. And so they show that instead you need to renormalize this slightly, and then like, well, based on compatibility conjectures for geometric Langlands, this should give you a commutative diagram. Yeah, so the idea is somehow like this, just you're forced to consider it because like even though this side is very hard to see at the level of classically, like it's hard to see like duality classically. Like I guess in the geometric picture it should be something very fundamental, and then like it turns out you can at least like define what this thing is at the level of functions. And so yeah, I would still be interested in like figuring out like what role this plays. Yeah, so I'll stop there. Sorry for going over. Yeah, I mentioned at some earlier point, currently there is no reason, just that I used a lot of other letters, and then L was the next one in the alphabet. Yeah. Well, in some sense, L is, with respect to like the Peterson inner product, it's self-adjoint. Although, like as an operator itself, it's not self-adjoint as an operator, but kind of formally it has that property. But yeah, I guess there is probably there's like a question of what like the actual like function analytic adjoint is.